We're going to move on to a new data structure today. Binary search trees are another option for implementing a data structure like a list or a table. We learned recently that hash tables can attain big O of 1 time complexity for insert, search, and delete, but they came with their own host of disadvantages. As the table fills up, performance can often degrade to not O of 1. Their inner workings were complicated and never really guaranteed to work. And one disadvantage that I didn't really touch on last class is that they're bad at in-order traversal. If you wanted to print all of the items in a hash table, which you probably will have to do for assignment 3 near the end, there's no good way to do it. Recall that hash tables use an array, and that array isn't ordered in any particular way. Based on how the keys are generated, hashed, there will probably be gaps between elements in the hash table, meaning that if you wanted to print them all, you have to go through the whole array every time. This is like O of n, and like for real O of n, because you're going to go through every item. And that's unordered. You don't really have control over how your keys will be distributed in a hash table. So if you wanted to go through all the items in some sort of order, like if you wanted to do that bookshelf example with the authors listed in alphabetical order, the best you could do is copy all of the stuff in the hash table into a sortable data structure, like an array, sort the array, and then print from there. And the time complexity would be O of n log n. I'm just going to write down that's a O of n copy plus O of n log n sort and this notation is going to be kind of weird because these sets of functions represented by asymptotic notation aren't really objects that can be added to each other, but it should still look pretty good intuitively. When I say O of n plus O of n log n equals O of n log n, what I'm really saying is that any function in O of n plus any function in O of n log n equals some function in O of n log n. Cool. So, hash tables, they're fast most of the time, but they're complicated and you can't traverse them. To solve this problem, we're going to look at a data structure called binary search trees. But before we talk about binary search trees, we need to talk about trees. And before we talk about trees, we need to talk about graphs. It's definitions all the way down. By the way, this is kind of setting the tone for the rest of the course. We are going to be drawing circles and lines for the entire rest of the course. So you should get really used to these fundamental definitions because they're going to be a part of every single data structure in the rest of the course. So a graph comprises a set of nodes, also called vertices. I'm going to switch the terms that I'm using all the time, so make sure you know both. So nodes and a set of edges where each edge connects a pair of nodes. So the 3 drawings at the bottom of this slide, these are all graphs. The first 2 have no edges, they just have nodes. and the last one has 3 nodes connected by 3 edges. A graph with no nodes is also a valid graph. It would just be a blank space. But you can't have edges without nodes because edges can only exist in connecting a node to another. I'm going to go into more detail about graphs when we actually study graphs as an ADT, because you probably learned about them in a discrete math course, but in case you haven't, these are used to model basically any situation where there are things and relationships between those things. A go-to example is nodes being buildings and edges being roads between them. And then you could use a bunch of fancy algorithms on those graphs to do things like figure out an optimal driving route from one location to another. But we're not really going to talk about that for now. We're going to talk about a specific type of graph, a tree, and then get to the generalization, like graphs in general, later. One more definition we need before introducing what a tree is. The edges in a graph can be directed, where an edge goes just in one direction specifically from one node to another. Maybe think of these as one-way streets. In this example, this edge goes, I guess you could say, from node A to node B, but not from node B to node A. I'm not going to focus on this very much, both because it'll become a lot more meaningful when we actually discuss graphs, and because we're kind of about to forget about the fact that graphs can be directed. You see, a tree is a directed graph with no cycles, but conventionally we don't draw arrows on the edges. We just draw the vertices and the edges in such a way that the ordering is implied. All directions are assumed to flow downward. So if you wanted to deliberately draw the directions, you would do so like this. None of these arrows are going to point up, just sort of by definition of a tree. So that's what we mean by it being a directed graph, but no cycles deserves some explanation. A cycle in a graph is when you can get from one node to itself by following edges along a graph. This graph has a cycle. In fact, it has a directed cycle. If I label the nodes like this, I can go from A to B, and then B to C, and then C back to A. I'd be walking in a circle from my start point back to my start point, and that's a cycle. Trees don't have that. If you wanted to start at A, go somewhere, and then go back to B without just reversing, no, you can't do that. So if you're trying to tell whether a graph is a tree or not, look for those sort of circles of edges. So like something like this would be a directed cycle. I drew another arrow on the edge from B to F to denote there being paths from both B to F and F to B. But in practice, again, we won't really have to worry about the directed nature of trees. There are a few terms you need to know. The root is the node at the top of the tree. It's the one node in the tree that has no edges going into it. I know I just said to disregard the directed nature of trees, but please briefly regard the directed nature of trees. Every node has at least one edge pointing into it, except for the root. And yes, the root is at the top of the tree, even though this is not how trees work in real life. There's a common joke that computer scientists draw trees like this because they've never seen a tree in real life. Yeah, we're gonna see lots of other tree metaphorical names, but also mixed in with family metaphors. It's weird, but all these names are chosen for a reason because they do make intuitive sense within their metaphors. We're going to go back to tree metaphors soon, but for now, we say that a node is a parent of another when there's a directed edge from the parent to the node that it is a parent of, which we call the child. So in this case, A is the parent of C. And also, like, A is the parent of D, C is the parent of G. Any pair of nodes that have that line moving downward into them have that parent-child relationship. Generalizing this, we say that one node is an ancestor of another if it's like a parent of a parent of a parent. So in this case, A is an ancestor of K, and likewise, K is a descendant of A, because there's a sequence of directed edges from A to K. As a negative example, E is not a descendant of A because, E is a descendant of A. E is not a descendant of C because there's no edge moving downward from C to E. If you start at C and can only go downward through the tree, you can't reach E. So E is not a descendant of C. Yeah.
Can H be a descendant of E? I'm just thinking because it says a sequence of directed edges, and there's only one directed edge, so this is still...
Yeah, that sequence can be one edge long. So yeah, even though H is the child of E, it is also a descendant of E, just like a direct descendant. All of the children of a node are siblings. See how those terms fit together? In this case, B, C, and D are all siblings because they all have the same parent. All right, yeah, back to tree metaphors. The nodes that have no children are called leaves. Guess we don't have a good word for that in the family metaphor, so we contrast these with the root, which all nodes are descendants of. The leaves are at the very, don't want to say edges, the very ends of the tree. And then this term's kind of lame because it's not really part of any metaphor. Any node that isn't a leaf is an interior node. You could think of the leaves being on the outside of the tree and the interior nodes being on the inside. In this example, all the nodes highlighted red are leaves and the rest are interior. Yeah, I think this lecture just has a whole bunch of definitions, and then we're going to actually get into the data structure later. the subtree rooted at a given node. Wait. Oh yeah, the subtree rooted at a given node consists of that node and all of its descendants, and it's another tree. So each child of the root is another subtree. Like, this is a subtree, and this is also a subtree. It's a very simple tree. Surprised it's not called a seed or a sapling or something. But yeah, it's a tree. And then, within subtrees, like say, this is all we know about. This is also a tree. It has a root, and thus all of its children are also subtrees. And until you reach a leaf, it's subtrees all the way down, which gives us a cool recursive definition of a tree. It is either a single node or a root node with one or more children, where each child is itself a root of a tree. I'm not really sure how to draw these subtrees in that little diagram. You're probably better off just imagining it. Getting closer to the actual topic of the lecture, binary search trees. We know what a tree is, and now a binary tree is a tree such that each node has at most 2 children. So you see, A has just 2 children, B and C. B also has 2 children, but C just has 1. And then the leaves, by definition, have 0 children. All of these instances are allowed by the definition of a binary tree, but it would be illegal if a node had 3 children or more. In a binary tree, each node can only have 2 children. The tree in the previous example is almost a binary tree. All but, I think, 2, unless I'm missing something, of the nodes have at most 2 children. Of course, A and G have 3 children, and I guess you could call that a trinary tree. Not a term that we ever use in this course, but it makes sense that it would be. This number 2 is going to be very important for, like, why we should care about the data structure. Remember the term binary. Spoiler alert, it's going to let us use binary search. But I'm probably getting ahead of myself. Binary trees have a cool recursive definition similar to those of trees. A binary tree is either a single node, or it's a node with at most 2 children, each of which are the root of another binary tree. Implementing binary search trees is straightforward. They're generally implemented using an internal node class. We have each node containing pointers to its left and right children, as well as some data. And then the binary tree itself maintains a pointer to its root node. This should remind you of a very similar data structure, the linked list. In that, each node contains some data and a pointer to one more node, the next node in sequence. And then the linked list class itself contained a pointer to the first node. This is just a slight generalization of that, except instead of each node having a next node, each node has a left child and a right child. So this slide finally finishes introducing the data structure. We learned about trees and the graphs we needed to understand to know what a tree is, and talked about what makes a tree binary. Now, it's time to justify the word search and introduce the binary search tree property. So if X is any node in the above binary tree, then the binary search tree property states that all of the data in the nodes in the left subtree needs to be less than that node's data, and all the data in the node's right subtree needs to be greater. So we got our root node 5. Each number in the left side is less than 5, and each number on the right side is greater than 5. And this property applies to every node in the binary search tree. We have 3 here. Every number on the left subtree is less than 3. Every number in the right subtree is greater than 3. When a node has only one child, or even 0, the definition can still hold. We just say that one of those conditions is vacuously true. In this case, all of the items in the left subtree are less than the root, and then right subtree, well, technically there isn't one, but by the way that implications work in math, if you have an empty set, then any property you're talking about is true for that set. So technically, every number or every data item in the right subtree of 2 is greater than 2. All 0 of them. So it works. So if a binary tree satisfies the binary search tree property, we call it a binary search tree, or BST. The subtree rooted at any node in a binary tree or binary search tree is also a binary search tree, which gives us a nice recursive definition. A binary search tree is either a single node or it's a binary tree, maybe defined recursively, such that all the data in the left descendants is less than the root's data, and all the data in the right descendant is greater than the root's data. And that gives us, that doesn't imply this. We need the extra condition that the subtrees rooted at the root's left and right children are themselves binary search trees. So that's the definition of a data structure, but all we have so far is really just a cool way of arranging numbers on a page. We haven't really done anything. We have the way that the data will be stored and an idea of how that structure will be implemented. But of course, the operations of any data structure or ADT are the important part. And I think we'll have to go through some sort of preliminary stuff like finding minimums, maximums, and also doing insertions. Soon, though, we'll see that this allows for traversal and searching that is quite fast. The searches aren't quite as fast as in a hash table, but the fact that traversals are possible really at all makes them distinct. So think about this for a few moments. You have a binary search tree. You have an implementation of them where each node has data and then pointers to its left and right children. How would you find the minimum and how would you find the maximum? I'm just letting you think about it. All right, thought about it? A key thing to notice here is that the minimum and maximum are on the extreme ends of the binary tree. Because the left side of any tree has the smaller values and the right side has the larger values, the smallest will be the leftmost value and the largest will be the rightmost. How do you get to the leftmost or rightmost value? Just keep moving left. Of course, this might be slightly tricky when you're actually writing code for this, but the idea is simple. You have some sort of loop, and then it keeps doing move left, move left, move left, move left. Something like while left is not equal to null to find the minimum, and likewise moving right repeatedly for the maximum. You can do this iteratively or recursively. The idea that I just sort of touched upon was iterative because it used a loop, but you could totally imagine a recursive minimum or maximum function that calls itself with a subtree. So using minimum specifically, we would start at the root node, move left, and then run the algorithm again for the subtree on the left. Start at the root node, move left, and see if my app even lets me zoom in far enough to rub this in. Start at the root node, move left, call the function again on that subtree, start at the root node, move, oh no, there's no left subtree. That means that we've reached the leftmost node and thus the minimum. And you would do the same for the maximum. And also take a moment to compare this to hash tables, because like on paper they are faster than binary search trees. But say you wanted to find a minimum value in a hash table, maybe the fish with the alphabetically first name, you'd be hopeless. Your best bet would be to go through the entire hash table, comparing everything until you've seen everything and to just remember a minimum, which, as we will see later and like kind of sort of prove later, that is asymptotically something that takes longer than going through part of the tree. But again, getting ahead of myself. Simple, comparatively simple topic. This is a lot easier than asymptotic notation. Since we still have half an hour left, I'm going to get started on the next lecture. Note that if I get significantly ahead of the lecture schedule, this will not affect the coverage on quizzes. So the slides I just opened, these are Wednesday's class, and the quiz will cover up to the end of this lecture, even if I get to the next lecture's file during tomorrow's class. recall the stuff that we talked about like a minute ago? Yeah, we're going to talk about searches finally. So you might remember forever ago, like earlier this week, I was talking about how linked lists are useful because they allocate data dynamically as needed. And so you don't need to decide the size of the structure when you create it, unlike what you have to do for arrays. However, just the way that linked lists work meant that it wasn't possible to efficiently search the linked list. You could only ever start at the first node and then just keep searching every node iteratively, one after the other. A far cry from the very cool binary search algorithm that works on arrays, which takes advantage of the fact that you can access any element of an array in constant time to sort of jump around the array until you narrow it down to the thing you're looking for. Binary search trees sort of give you the best of both worlds. As sort of implied in the bit about implementation, this is a linked data structure. It consists of nodes that point to each other. When you insert a node into a binary tree, which we will cover later, the thing that you're inserting or you create a new node for that thing, and you add it to the tree dynamically. I guess I shouldn't have said when you insert a new node. When you insert a new data item, it creates a new node dynamically. Whatever. It has the same advantage of linked lists. And because of how this is structured, we have access to binary search, which means that we can search for items inside of this data structure in big O of log n time, as opposed to big O of n, which is kind of a huge deal. Like, graph x and log of x into a graphing calculator if you're not impressed yet, because the logarithmic function goes so much slower than the linear function. And techniques like these are basically what make things like searching for a YouTube video or searching for a user on a social network even possible, because linearly searching through millions of users would be super slow, and allocating memory in advance for millions of users would be super clunky. Something like this is how searching through these complicated data sets are able to work. So, suppose you're searching this binary search tree for the value 32. We always start at the root because that's the only node we initially have access to. And then we narrow the search space down very similarly to binary search. So in binary search, we would find that 32 is greater than 18, so it must be on the right side of the array. Narrowed it down to rule out a bunch of array indices. Likewise, we know that 32 is greater than 18, so it must be in the right subtree. So you go right. You continue searching, starting at the root of the right subtree. Then 32 is greater than 27, so we move right again. Focus on this subtree. 32 is less than 36, so it must be in the left subtree of the root. And then we found it. Notice how we didn't have to worry about the nodes on the left or even the left of the right subtree at all. We ruled out half of the potential positions on every step, which is way cooler than ruling out one possible position every step. The next few slides just go through this highlighting. I think zooming in is way cooler. But yeah, we found it. A failed search looks very similar. We just search for the thing that doesn't end up being in the data structure, and then give up when we find that the direction we're trying to go in has no, subtree. So suppose we're looking for the value 14. It's less than 18, so we go to the left. Then we compare it to 12. It's greater than 12, so we go right. Compare it to 15. It's less than 15, so we want to go to the left, but there's nothing there. And because of how binary search trees are structured, we can conclude that the value 14 is just not in the tree. In the implementation of this would be a matter of checking that the pointer to one of the children, in this case the left child, is null. This is another exercise to the reader that I'm pretty sure will just be an assignment question. I don't remember if assignment 4 is going to require to write searches iteratively, but it's going to involve searches. So if you want to study binary search trees ahead of time, write the search algorithm. Now we know that if you have a binary tree, you can search through it really quickly. But that initial condition of once you have a binary tree is carrying a lot of weight. So we need to figure out how to actually construct one. Adding a new entry to a binary search tree requires you to insert it in such a way that preserves the binary search tree property. In this case, this makes insertions a bit slower than on a linked list or even an unsorted array. But it's still way faster than insertion in a sorted array, which is the only other data structure that we know of that allows for logarithmic time searches. Let's insert the value 30. The insert operation basically begins with a search. We're going to search for 30, fail, and then insert a node containing 30 in the space where we expected to see the value 30. I think it's going to go here. But let's go through the search anyway. Start at 18. 30 is greater than 18, so we move to the right subtree. 30 is greater than 27, so we move to the right subtree. 30 is less than 36, so we move to the left subtree. And then finally, 30 is less than 32, so we attempt to move to the left subtree, but it doesn't exist. The search technically failed. But this is the insert algorithm, not the search algorithm. So once the search has failed, we just insert the value where we expected to see it. And then any future searches for that value will be able to find it where it was supposed to be. Maybe wondering about duplicates in a binary search tree. And if anyone asks, I'm just going to be like, I don't know. It depends on the implementation. This will have something to do with the actual application that you're making data structures for. If you, wait a minute. Okay, so if you're allowing for duplicates, I guess you could put it in either the left or right subtrees. But that messes up the binary search tree property. Or does it? Or yeah, each of these subtrees would have their own left and right children, which makes for two possibilities for where this item you're looking for is. You can no longer rely on just the left and right pointers to give you a path directly from root to the thing you're looking for. So you would have to probably recursively call your method multiple times for all of these duplicate nodes. It would get messy, but it would be workable. Binary search trees work best, though, if you don't allow for duplicates, though. Just make this insert operation fail, return false or something, if you try to insert a value twice in a row, because then the binary search tree property will be preserved. If you want fast searches and you're using a data set that allows for duplicate keys, you should probably just use another data structure. And actually, I want to check out the binary search tree property. Oh yeah, this used strict inequalities. So this doesn't necessarily invalidate any of the stuff I said about keeping duplicate keys and then just sort of branching out your search to check both duplicates of a key. But the binary search tree property discussed in this class, as defined in this class, relies on strict inequalities and thus breaks if you have duplicate keys. So again, while it is possible to implement the stuff I described, it would break the definition we're learning in this class. So don't do it. Here's an exercise for you. If you're following along with the slides and want to study later, maybe like cover your eyes while looking at the following slide, because this is a nice little practice exercise. Insert the values 16, 17, and 23 in that order into the binary search tree. The order of inserting elements may or may not matter. Or you might get a different result if you insert the values in order 17, 16, 23. But will you? Woo! There we go. I don't know. I didn't read the slide. But you should, as practice. Now this operation successor finds the value that basically comes after a specific other value. The value that would appear immediately after it if we listed all the values in the tree in ascending order. Another way to talk about the successor of a value k is that it is the lowest value that is greater than k in the tree. The use of this operation isn't immediately obvious. Like, it is immediately obvious why we would want to insert and search into the tree, but finding the successor, unless we're just looking for perfect feature parity with linked lists, it's not really clear why you would need this. Turns out it's totally necessary for the delete algorithm, which will be covered in the next lecture. Or maybe even, no, I think later in this lecture, but then finished in the next lecture. Anywho, we're going to look at a few successors, just find them manually, and hopefully, as we're looking at the successors of different nodes, you sort of start to get an idea of how you might write an algorithm to do this in general. So, what's the successor of 36? Well, there are only two values in the tree that are greater than 36, and one of them is obviously less than the other. So I would say the next one is 39. 27. Well, again, we look at the right subtree, and we can just eyeball what the smallest value is. It's 32. This is a pretty big tree. It might start to get difficult to just look at it and see what the successor is. But this is when I hope the gears are starting to turn about how you might want to write an algorithm for this. The successor to 18 is the smallest value that is greater than 18. Thus, the smallest value in its right subtree, 20. Smallest value in right subtree. Well, we kind of started off our discussion of binary search trees by making a minimum and a maximum algorithm. So, accessing the right subtree is trivial. It's just accessing the node's right pointer. And then we already know how to find the minimum value in a binary tree. Just keep going to the left. And that works. The successor of 18 is the lowest value in 18's right subtree. So we're done. We can just apply our algorithm to the rest of these. Not quite. Our next value, 21, doesn't have a right subtree. So this breaks the algorithm that we thought we just discovered. The successor operation will turn out to have multiple cases based on which children the nodes we're looking at even have. In this case, we could still just eyeball it. The successor to 21 is 25, obviously. So maybe our algorithm will check out the parent of a node that doesn't have a right child. So let's try applying that to 9. The parent of 9 is 6, which is not greater than 9. Bummer. So we already found something that works in general for nodes that have right children, but for nodes that don't, we're still on the drawing board. I'm just gonna eyeball this one. The successor to 9 is 12. You could tell by the way that it is. And then the successor for 17, that one I can see is 18. And it's probably still not clear how exactly you're supposed to write code to find the successor of a node that doesn't have a right child. Turns out you have to climb back through the ancestors of that node, and then the successor will be the first ancestor that is a left child of its parent. If you look at past examples, you see that this just works. For 21, 25 is 21's immediate ancestor, and 25 is the left child of its parent. So everything about that is true, and 25 is the successor. Just works. Likewise, 9's parent. Oh wait. Right. This time we find an ancestor that's a left child. Oh, right. I missed a detail. I just need to read the next slide. If X does not have a right child, we have to climb back up through the ancestors of X until the first time we find an ancestor that is a left child of its parent. Then, that ancestor's parent contains the successor. So in this case, 9's parent is the left child of its parent. So that parent contains a successor. And then going back to 21, I didn't really explicitly think about this until now, but I guess that for this explanation to work, nodes have to be considered their own ancestors. Kind of weird. You'd say that the parent is one edge away, an ancestor, and a node to itself is 0 edges away, but still an ancestor. So if you're searching for 21 successor, the first ancestor of 21, that is the left child of its parent, is 21. And then its parent is the successor. Phew. And luckily for 17, this works exactly as you'd expect. Just keep going through ancestors. The first ancestor to be a left child of its parent is 12, so that parent, 18, is the successor. This gives us the algorithm for the successor operation. Not very useful on its own. You might think it's good for iteration, but in practice, there are better ways to iterate than repeatedly finding successors. However, this will be absolutely necessary for the delete operation. less than a minute left. I'm going to cut it off here and we'll learn about the delete operation tomorrow. See y'all later.